This is a three-part series on the backpropagation algorithm. The backpropagation algorithm is at the heart of all neural network learning. In fact, the popularity of neural networks mostly began only when the backpropagation algorithm became popularized. Now, the backpropagation algorithm is essentially a combination of some simple rules of differential calculus with dynamic programming. These simple rules of differential calculus correspond to the univariate chain rule and the multivariate chain rule. Now, if you did not use dynamic programming, that is, if you did not use backpropagation, it is still possible to compute the loss derivatives of the output of a neural network with respect to intermediate variables. The main sticking point is that it would require exponential time. However, it is useful to explore this exponential time algorithm in which all we use is some simple high school mathematics. That is just your univariate chain rule and your multivariate chain rule in order to compute the loss derivatives of the output with respect to the weights of the neural network. Then in the next part of this series, we will see what dynamic programming, that is what backpropagation brings to the table in making these computations efficient. So why do we need backpropagation? As we saw in previous lectures, any kind of learning requires you to compute the partial derivative of the loss function with respect to each intermediate weight. It is with the use of these partial derivatives that you can perform gradient descent. A specific example that we showed in previous lectures was the case of the perceptron. In the case of the perceptron, it is a simple matter in order to perform gradient descent because it is easy to compute the partial derivative of the loss with respect to the weight. However, this is not quite a simple matter with multilayer architectures. The multilayer architectures are essentially expressed as computational graphs. What is a computational graph? A computational graph is a directed acyclic graph in which each node computes a function of its incoming node variables. So there's a variable in each node. The graph is a directed acyclic graph where the edges tell you the direction of the computations and each node computes a function of its incoming nodes. A neural network is a special case of a computational graph. Here, each node computes a combination of a linear vector multiplication, that's a vector dot product. So you have w dot x if you have a weight vector associated with the node, and then you might have a nonlinear activation function. So for example, it might be the sigmoid function. Now, the problem is that this computational graph might have many layers, and the output will likely be a very complicated composition function of each intermediate weight in the network. Now note that this complex composition function, it will be hard to even express it neatly in closed form. And this is what makes it difficult to differentiate. So just to explain what I mean by this, let me just give you an idea of the simplest possible computational graph containing only two nodes. So you have an input W and you have two nodes in a path. So you have two computational nodes along with the input W. So the first node, it computes y is equal to GW. And the second node computes the output, which is the function of y. So it's a function of whatever was computed by the first node. So obviously, your overall composition function is f of GW. This is recursive nesting, and that's natural for computation graphs. Now let's look at what happens if we set f and g just to the simple sigmoid function, which is actually an activation function that is used very frequently in computation graphs. Now, if you set f and g to the sigmoid function, what you have is the expression shown in equation 1. As you can see, this expression already looks pretty ugly. And if you had to differentiate it, it probably can be done. It's just that it's a bit ugly to do. In general, a computational graph will obviously, of a neural network, will obviously be a lot more complicated than a computational graph containing just two nodes, which is what I showed you. And increasing the path length will increase your level of recursive nesting, which makes it more difficult. However, in practice, in these kinds of recursive compositions, we use a rule that we learned in high school. We don't actually express it in closed form. We can use what is called the univariate chain rule of differential calculus. So here I've shown an example of the univariate chain rule in action. So you have a computational graph containing two nodes. The first node that computes GW, which is the square of the input weight. So you have W and it computes the square of that. And the output is Y is GW. And the output is the cosine of that. So the final output O, which is the final output of the full computational graph, is cosine of W square. So now, what you really want to do is that you want to compute the partial derivative of O with respect to W. Now, the way to do it is to use the univariate chain rule. So the idea here is that first you will compute the derivative of Fy with respect to its input Y. Note that this is a local derivative. You are using the input of the node computing the function Fy with, you're computing the the derivative of the function Fy with respect to its direct input Y. And similarly, you're computing the derivative of the function GW with respect to its direct input W, which is easy to compute. So the derivative of Fy with respect to Y is given by minus sine Y, and the derivative of GW with respect to W is given by 2W. So by the univariate chain rule, it's the product of the local derivatives. You get minus 2W sine Y, which is minus 2W sine W square. And this approach is used very commonly in differential calculus. In fact, in traditional machine learning, you probably use it very frequently. However, in neural network, the univariate chain rule is not enough. Typically, what happens is that they contain multiple nodes in each layer. A neural network will contain multiple nodes in each layer, and each node computes a multivariate function f of its incoming node. So let's say the incoming nodes, they compute G1 through Gk. Then the composition function computed by that node is f of G1 through Gk. But the multivariate chain rule is similar to the univariate chain rule. What you can do in the multivariate chain rule is that you can compute the derivative of the function with respect to each gi and then multiply with the partial derivative of gi with respect to w. And then we aggregate it over all k nodes. So let's look at an example of the multivariate chain rule in action. So here I have a simple function cosine w square plus sine w square. So the input, as you can see, is w. The very first node, it computes fw is equal to w square, and then it feeds this same input into two nodes, but I have denoted them by two different input variables to distinguish them. One is a y and the other is z. So the top one with its input y is equal to fw, which is basically w square. It computes the cosine of y. And the lower one, it computes the function h, which is the sine of z, its input. Then what you do is that for each of these, you have a final node which adds them. So that's the addition. That computation node just performs a simple addition of its two inputs. So your output is just the sum of cosine w square plus sine w square. Now let's say you wanted to find the partial derivative of O with respect to W. And we can use the multivariate chain rule. So basically what you do is that you differentiate along for the node, for the final output node, you differentiate with respect to its two incoming nodes. And then similarly for each of the nodes previous to it, you differentiate it with respect to both and you add them. What you'll finally find is that what you're really doing in this case is that you are taking each path in this network. And then you're computing the local derivative along each path in the network and you're adding them. So you're doing exactly the same thing that you did in the univariate chain rule, except that you are doing the same thing over all paths in the network. In the previous case, you only had one path in the network, so you have to do it only once. Here you have to identify all the paths in the network, do this exact same process as the univariate chain rule over all the paths and add them. So that brings us to what is called the pathwise aggregation lemma. So let's say that you want to compute the derivative of the output O with respect to a variable W, and a non-null set of paths exist from this W to O. So what you're going to do in this computational graph is that the first step that you're going to do is that you're going to compute the local gradient of the node with variable j. That's the endpoint of the edge with respect to its source, with respect to yi. Okay, so let's say the variables yi exist in node I. So zij is the partial derivative of the destination of the edge with respect to the variable in the source of the edge. And that gives you zij. And all you do really, all that the path aggregation lemma says is that the derivative of the output with respect to w is simply obtained by computing the product of the local gradients along each path in P and then summing up this product over all paths. Now, note that each zij is easy to compute because all that each zij has to do is that it has to compute a local derivative. So it has to look at the function computed at a particular node and just compute the partial derivative of the function with respect to its immediate predecessor. So this brings us to a natural exponential time algorithm for computing partial derivatives, and you can in fact use this algorithm for learning the derivatives of the output with respect to various intermediate weights. So the first thing that you're going to do is that you're going to use your computational graph to compute the values within the nodes, within each node in a forward phase. So let's say yi is the variable within each node I. Then what you're going to do is that you're going to compute the local derivative zij, which for each edge ij in your computational graph. That's the derivative of yj with respect to yi. Note that this is completely local and you can do it without knowing what's happening anywhere else in the graph. Then what you're going to do is that you're going to identify the set P of all paths from the node with variable w to the node O. And for each path, you will compute this product of local derivative, the zij that you computed. And then you're going to add up these values over all paths P in P. And that's it. You have a way to compute the derivative of the output with respect to any intermediate weight in your computational graph. Of course, this is a very inefficient way of doing things. And what's going to happen is that when you have a computational graph with many layers and many nodes per layer, this is going to blow up on you. And I'll give you a very simple example of a computational graph with 5 layers. So here I have shown a computational graph with 5 layers, and what each node does is that it computes the product of its 2 inputs. Okay, so each layer has 2 nodes and each node is computing the product of its 2 inputs. So clearly the very first layer, it only has w because it only has 1 input. The next layer, it's w times w, so it's w square. The next layer is w square times w, so it's w to the power 4, and so on. And the output is w to the power 32. And you want to compute the derivative of the output with respect to the input. Now in this case, the output is expressed in closed form. So obviously we don't really need to use our exponential time algorithm. We can compute the derivative straight away. But we want to actually use this algorithm just to see, just as a case study as to what happens when we use this algorithm. Now note that since each node is computing the product of its inputs, the partial derivative of a product of xy with respect to one input x is really the other input y. Okay, so actually that's why I chose this particular kind of function, because it's rather easy to show you what goes on. So computing the product of partial derivatives along a path is equivalent to computing the product of values along the only other node disjoint path. So you know, in this graph, if you take any particular path from the weight w to the output, there's exactly one other node disjoint path, because each layer contains 2 nodes. So in this particular case, because of the way the partial derivative works, it has a particular simple form, what the product of the derivative along a path is. It's simply equal to the product of the values on the complementary path. Okay, so in this case, the aggregative product of partial derivatives equals aggregating the product of values, just in this particular case, and let's see how we can do that. So here, I have shown that aggregation of the values. So you have 32 possible paths because in each layer you have two possible nodes. So you can you have two possibilities in each node in each layer for picking one of the two options. So you'll have 2 to the power 5 paths in this case. So each of these 32 paths you multiply the product of the values. So it's so the first layer you have W, second layer W squared, W4, W8, and when you take the product, you get W to the power 31. So each path is going to give you a value of W to the power 31. But since there are 32 paths, you are going to get 32 W to the power 31. Now, of course, this is consistent with what you already know what the derivative of this is. But the key point is that you had to do this 32 times. And this is just a very simple graph with 2 nodes in each layer, only 5 layers. Real world neural networks are far more complex with this, and so with increasing depth, increasing number of nodes in each layer, this becomes impractical. So just to give you an idea, if you had a network with just 3 layers and 100 nodes in each layer, this is a very modest network by modern standards, you will get 1,000,000 paths. Okay, so it's going to get very impractical if you try to compute and that's just to compute the derivative for one weight in the network. Then you have to do this for all weights in the network. But that being said, you might not be aware that this exponential time algorithm is something that you actually unconsciously use when you do traditional machine learning. So anytime in traditional machine learning you have some complex composition function, you actually use the chain rule of differential calculus. You actually use the univariate and the multivariate chain rule, and you actually explicitly materialize all these derivatives as separate terms. Sometimes you may use a few heuristic tricks to make it a bit shorter, but by and large, you do the full manual differentiation. Now, if you had a really complex function, the kind of complex function that a neural network computes, the algebraic expression for the derivative, it might not even fit the paper that you write on. So that's what explains why most of traditional machine learning, it's a special case of neural network, but it's a case of very shallow neural model, because it's simply not possible to even practically compute the derivatives using traditional calculus methods if you were to do it using the exponential time algorithm. And what backpropagation really brings to the table, what its beauty is that it brings a dynamic programming idea which rescues us from this complexity. And this will be the topic of the second part of our backpropagation lecture. In this part of the lecture, we will discuss how to make the loss derivative computation in a neural network much more efficient. The functions computed by a neural network are complex composition functions which have a special type of structure. We will discuss how this special type of structure can be leveraged by a dynamic programming algorithm to perform the loss derivative computation in polynomial time. The name of this dynamic programming algorithm is backpropagation. So, what is the special structure of the composition functions computed by neural networks? Neural networks are structured as computational graphs in which there is a lot of repetitiveness caused by the node appearing in multiple paths. So, for example, if a node appears in an early layer, then that function is reused by multiple paths downstream. As a result of this, the most natural way you would differentiate a composition function with the use of the multivariate chain rule is not the most efficient way to do it. In fact, when you manually differentiate such a function with the chain rule, you are essentially using the exponential time algorithm. So in order to understand this point, let us revisit an example that we discussed in part 1 of this lecture. So imagine the function fw is equal to sine w square plus cosine w square. Now, we saw the computation graph for this function in part 1 of this lecture. It is a 4-node computation graph in which the function w square is the very first function that is computed, and this is used downstream by both the sine and the cosine. When you manually differentiate this function, you are going to differentiate both the sines and the cosines separately, and then in each case you are going to differentiate w square. So you're going to differentiate w square twice. It is this repetitiveness in the computation which causes the exponential complexity of the naive algorithm that we discussed in part 1 of this lecture. The key in dynamic programming is to collapse these repetitive computations to reduce the exponential complexity into polynomial complexity. So let us revisit some of the notations that we used in the first part of the lecture. So here we have a computation graph with an input weight W and an output O, and each node I has a variable yi inside it. So here, for example, in this particular graph, I have shown y4 as a variable for node 4 and y6 as a variable for node 6. And the derivative of yj with respect to yi, we label the edge as zij. So here, for example, I have labeled the edge 4, 6 with z4, 6, which is essentially the partial derivative of the variable y6 with respect to the variable y4. So in this computation graph, suppose you needed to compute the partial derivative of the output O with respect to the input weight W. The naive way to do it would be to just find all the paths in this graph from the weight W to O, compute the product of zij's of all the edges on all these paths and just add them. So that value is the partial derivative of O with respect to W, and we will denote it by SWO. That is the notation that we will use for our dynamic programming update. Now, dynamic programming is an approach which is extensively used for exponentially aggregative path-centric functions between source sinks pairs, or even functions from all nodes to sinks or from the source to all nodes. So one specific example is the longest path problem in a graph. Now this problem is known to be NP-hard. However, it's polynomially time solvable on a directed acyclic graph if you use dynamic programming. In general, various kinds of maximization and summation functions on paths in directed acyclic graphs can be computed using dynamic programming. And the general approach in all of these methods is to start at either the source node or the sink node and recursively compute the relevant function over paths of increasing length by reusing intermediate computations. So it is in this reusing of intermediate computations that the savings are achieved. So in this case, what is our path-centric function? Our path-centric function we already introduced in the previous slide. It is essentially SWO, which is the aggregation of the product of zij's over all paths. So here, of course, since you want to compute SWO for various nodes with respect to O, the backward directions makes more sense. So you want to really compute not just SWO, you want to compute SIO for all nodes I with respect to O. So the partial of O with respect to all nodes I. So in this case, we really want to do our dynamic programming update in the backwards direction by starting at the node O and moving backwards. So what is this dynamic programming update? So let us consider the case where AI is a set of nodes at the ends of outgoing edges from node I. So SWI, which is essentially the partial derivative of the output O with respect to the variable in node I, it's an intermediate variable indicating the same path aggregative function from the node I to node O. Now, what you can show is that this SIO is given by the sum of the product of SJO and Zij for all nodes J which are outgoing from node I, which are at the ends of outgoing edges from node I. And the way you can easily show this result is by just looking at this path-centric function SWO. If you substitute the right-hand side on both sides of equation 4 here, you can show that this equation is satisfied. So I will leave this as an exercise for you. So once you have this dynamic programming update, it actually becomes very easy to compute this path aggregative function. So first you initialize SOO to 1 because the partial derivative of the output with respect to itself is 1. Now note that here we are using SOO. In general, for neural networks, you'll have a loss function. So SOO may be some partial derivative of loss with respect to the output. But here, let's first look at a simple case where SOO is 1. And then you'll compute backwards. So then what you're going to do is that you're going to look at all the edges which have an incident edge on node O. You compute SIO for those edges using equation 4. Then you go backwards to the next layer and again use equation 4 and so on. So each node you have to perform this computation exactly once. And you can show that each edge you will visit exactly once. And in a time complexity equivalent to the number of edges in your network, you can perform this computation. So you will have SIO for all nodes including the weight W. So you will have all the partial derivatives that you want. Now, one point that I want to note is that if you look at equation 4, it's very familiar. The SIO, that's really the partial derivative of O with respect to the variable in node I. The SJO, that is really the partial derivative of node O with respect to the variable in node J. And the Zij is really the local partial derivative. That's the partial derivative of Yj with respect to Yi. This is exactly the multivariate chain rule. Now, it's not particularly surprising that we got the multivariate chain rule here because remember the exponential time algorithm, we had derived that in the first place using the multivariate chain rule. So we simply got that back in the dynamic programming update. The difference is that here you're using the multivariate chain rule in a particular order, in a particular backward direction, in a systematic way. And by doing so, you are reusing the work done in early iterations in later iterations. It is for this reason that you are able to save on the time complexity, you are able to reduce your exponential time complexity to polynomial time complexity. So now our discussion so far has focused on generic neural networks. Generic computational graphs. So one question arises is how does it apply to neural networks? How do we define a computational graph given a neural network? Now note that a computational graph is essentially a graph of variables. So what you need to do is you need to pick some of the intermediate variables in your neural network and define a computational graph based on these intermediate variables. Now, there are various ways you can pick intermediate variables. So, for example, remember that a node really computes two separate functions. First, it performs a linear transformation by doing a dot product with a weight matrix, and then it applies an activation function. So, you can use the hidden variable value, which is the post-activation value. That's one possibility as your intermediate variable in the computational graph. Or you can use the pre-activation value. That is the value after you perform the linear transformation but before you apply the activation function. That is below, you can see the AH I have shown. That's your pre-activation value. Now, or you can even have both variables. So you can create a computational graph which has both the pre-activation variable and the post-activation variables. And you can use that in order to use the dynamic programming update. Note that for the same neural network, you can compute the computational graph in multiple ways. And here I'm going to go through all of the possibilities just to show you that this particular broad idea of computational graphs, you can get different types of updates, but the end result is always equivalent. So let's first start with the pre-activation variables to create the computational graph. Now this is actually what you see in most textbooks. Typically, if you pick any textbook on neural network, this is the typical update that you will see. So in the pre-activation case, you want to compute delta IO, which is the derivative of the loss L at O with respect to the pre-activation variable at node I. Now, one thing I want to point out is that in neural networks, you always compute the loss derivatives of the with respect to the intermediate node variables. Okay, you don't directly compute it with respect to the weights because the loss derivative with respect to a weight ij from node I to node j is given by the product of the loss derivative with respect to the node at j and the computational graph variable at I. And I will leave it to you to work out why this is the case. This is just one further application of the univariate chain rule. You can show this. Now, So the key points is that now we need to define what our zij's are. So in our computational graph, we had these notations. We had zij's and we had some initialization points. That is SOO. So our zij is essentially the weight from I to j. Note that the local derivative of the pre-activation variable at node j with respect to node I, because we are multiplying by wij, it will contain wij, and also we are, because it's a pre-activation variable, we are applying the activation function at node I. So it's the derivative, phi I, the derivative is at node I, which will be different in the case of the post-activation function. We'll see that in the next slide. Similarly, initialize SOO as the derivative of the loss function as well as multiplied by the derivative of the activation at the output node O. Note that we are using the pre-activation variable at the output node 2 as the intermediate, so we also have to multiply by the derivative of the activation at node O. Now, given this, you can just straight away substitute it in the dynamic programming update that you had 2 slides ago. These ZIJs and these SJIs. So, when you substitute that, you get this update, this equation 5 over here, which is delta IO is given by phi prime I, sum of j element of AI, WJI, delta JO. This is exactly the update that you see in most textbooks for neural networks. But there's a different way of doing this update. So let's say you use the post-activation variables to create the computational graph. So here, the variables in the computational graph, the way you're defining are the hidden values after activation function application. So in this case, you define delta, we are using big delta, of loss L with respect to O, with respect to post-activation variable at node I. Now here, the only difference is that your Zij is defined differently. Because you are using the post-activation variable, your Zij is Wij multiplied by the derivative of the activation at node J. Note that in the previous slide, it was Zij was Wij multiplied by the derivative at I. Here, it's Zij multiplied by the derivative at j. And similarly, the initialization is slightly different because you are using the post-activation variable. It's simply the derivative of the loss function with respect to O. Here you had the derivative multiplied by phi prime O. That's the main difference here. And basically, after that, the updates are very similar. But you can see the form of the update here is slightly different. You can see that here you are using Wij delta Jo and phi prime j. So you can't really pull phi prime j out of the summation. Here you have note that you have pulled phi prime I out of the summation, which makes it a bit simpler, which is why they tend to use this one, this particular, the pre-activation variables in most textbooks. Now, you can even define a computational graph using variables for both pre-activation and post-activation variables. And this is a nice way of decoupling the linear multiplication and the activation operation. And this decoupling has other benefits because you can actually have a simplified approach in which each layer is treated as a single node with a vector variable. And the update can be computed in vector and matrix multiplication. So this is actually very convenient because when you look at real implementations of neural network backpropagation, they are done using matrix multiplication. So in GPUs, for example, you'll typically, that's how you would be doing things. So this, I will leave it to the next part of the backpropagation series, but I just wanted to briefly mention this point here. So I will mention two other small special cases, changes to backpropagation that you sometimes need. One is that here we assumed a simplification that the loss is incurred at single output node. In reality, the loss could be incurred at multiple output nodes. In fact, typically it is incurred at multiple output nodes. And in some cases, the penalties may even be applied to hidden nodes. That often happens in some cases where you are using regularization. So in the case of multiple output nodes, it is actually quite simple. One just has to add up the contribution of the different outputs in the backward phase. Now in the case where your penalty is in hidden nodes, again it's not very different. You perform the backpropagation as usual, but after, so assume you have a penalty at some node I. So after you have computed SIO using dynamic programming, you add a quote-unquote initialization value. This is the same type of initialization value that you would add to a true output node based on the penalty at that node. The main difference from an output node is that in the output node you add, that's what you initialize it at. So you start at 0. Here you start at whatever you have whatever you have computed using dynamic programming, and then you add it to that value. And then finally, you have many cases where you have shared weights. So you saw an example of autoencoders some lectures back where the encoder and decoder weights are shared. In fact, in many advanced neural architectures, shared weights are very common. Shared weights is a very good way of incorporate domain-specific insights within your neural network architecture. And this can be solved with a simple application of the chain rule. So what you do is that, let's say that you have a neural network and you have a R weights which are shared. So, and these W1 through WR are R copies of the same weight in the neural network. So what you do is that to compute the loss function with respect to the weight W, you apply the chain rule. Now note that the derivative of Wi with respect to W is just 1. So you're just left with the sum of the derivative of loss function with respect to the various weights. So all you have to do is that when you have shared weights, you just pretend that the weights are not shared. You perform backpropagation as usual, compute the derivatives with respect to each copy of the weight, and just add up those loss derivatives. That's all. That will give you the derivative with respect to the shared weight. And this is a very useful trick which we will use all the time at various points. So far we have only seen settings in which either pre-activation variables or post-activation variables are being used to define the computational graph. What this means is that in each node, we are performing a combination of a matrix multiplication and an activation function evaluation. The ordering of these two operations might be different in the two cases, but still both the two operations are being performed in these cases. In this part of the lecture, we will consider that case in which the computational graph is defined by both pre-activation variables and post-activation variables. Defining the computational graph in this way has the effect of decoupling the matrix multiplication operations and the activation function operations. Furthermore, we will consider a setting in which the nodes of the computational graph can perform vector-centric operations rather than scalar operations. This leads to a version of the backpropagation algorithm in which the entire algorithm can be performed in very efficient matrix-centric or vector-centric operations. In the previous part of this lecture, we saw how we can create multiple computational graphs from the same neural network. We saw how we can create a computational graph of pre-activation variables, and we derived the updates for these pre-activation variables. And we also derived the computational graph of post-activation variables together with the updates. All of these different methods are basically equivalent. In this part of the lecture, we will look at the case in which we have a computational graph containing both pre-activation variables and post-activation variables. Using both pre-activation variables and post-activation variables decouples the backpropagation updates for linear matrix multiplication and those for the activation function. From an implementation point of view, as we will see, this turns out to be quite convenient. The other different way in which we will look at computational graphs in this part of the lecture is that we will look at vector-wise computational graphs. So far, we have only looked at computational graph with scalar operations. That means the nodes contain scalar variables. Here, we will look at computational graphs in which the nodes contain vector variables. Now note that neural networks are typically constructed in layer-wise fashion. We can treat an entire layer of a neural network as a node with a vector variable. And then we want to use layer-wise operations on vectors. So for example, a linear matrix multiplication turns out to be a multiplication with a matrix. And an activation function turns out to be an element-wise application of an activation function on a vector. So in this case, we are also decoupling the linear matrix multiplications and the activation functions in separate layers. So just to show this pictorially, I have shown an example where I have shown layer I, decoupled layer I plus 1 and decoupled layer I plus 2. Note that between decoupled layer I and decoupled layer I plus 1, you are multiplying with the weight matrix W transpose. So you have a vector in decoupled layer I and you create a vector in decoupled layer I plus 1. Note that each of these rectangles is now a new node which contains vector variables. Similarly, from layer I plus 1, you apply the activation function element-wise to each element of the vector to create the decoupled layer I plus 2. So for example, you might be applying the sigmoid function to each variable in I plus 1 to create the layer I plus 2. Note that in many cases, when you are working with the activation function, the successive layers, the corresponding vectors in the nodes, they will have the same length. That is because the activation functions are typically one-to-one operations. Now, one point is that here you can see that this particular arrangement is also a kind of computational graph. The difference is that here the nodes contain vectors. The entire computational graph is just a single path, and the edges of this computational graph, they are vector to vector functions. Now note that backpropagation on such a computational graph actually is very simplified if you have knowledge of matrix calculus. In this case, because you have a single path, you can use the vector to vector chain rule to backpropagate on a single path. However, we will use a much simpler approach by using the framework we have already developed in previous lectures to derive these updates. These updates will be identical to the ones that you can derive using matrix calculus. Now, just to recap what we already discussed in the previous part of this lecture, the dynamic programming update, which is SPO, that's basically the partial derivative of the output with respect to the variable in node P, is given by the product of SQO with ZPQ, and where Q is from the next layer and you're summing it up over all nodes in the next layer. Now note that this is a scalar operation. We can convert this equation 8 into a vector-wise equation by stacking up all of the equations for all of the nodes in a particular layer. So imagine that SPO belongs to layer I. So for all of the nodes in layer I, you can write equation 8. So you can create a single column vector Gi whose elements are these different values of SPO. And similarly, you can create a column vector Gi plus 1 whose elements are the corresponding elements in the layer I plus 1, the SQOs in the I plus 1th layer. Now you can also create a matrix Z. Z basically contains the local partial derivative, that is small z pq. So it's a matrix. So what you can show that equation 8, when you stack it up in matrix form by creating these vectors, you get this equation Gi is equal to Z Gi plus 1. That's equation 9. Now what is this matrix Z? The pqth element is ZPQ, which is a partial derivative of the variable in node Q with respect to the variable in node P. This is essentially the transpose of the Jacobian. And in fact, we are going to use the notation J is equal to Z transpose in further slides. So here I've changed the notation a little bit, but basically what I'm stating in this slide is exactly the same as the previous slide. So consider layer I and layer I plus 1 with activation Zi and Zi plus 1. Now imagine that the kth activation in layer I plus 1 is obtained by applying an arbitrary function on the vector of activations on the layer I. So essentially you have Fk, which creates the kth activation in layer I plus 1, and it has a vector argument. So you define your Jacobian matrix entries JKR, which is the partial derivative of Fk, the kth element of the function, with respect to the rth component of the activations in layer I. So what we already showed in the previous slide is that the backpropagated update is essentially given by J transpose, the transpose of the Jacobian multiplied by Gi plus 1. Now, one point that I would like to make is that you remember that I had already discussed a few slides back that in this kind of computational graph containing a single path, you can also derive this backpropagation updates by using the chain rule as it applies to vector operations. Well, if you applied the chain rules to vector operations for Gi and Gi plus 1, you would essentially get the Jacobian. So you would get exactly equation 11 if you use that. That would just be a simpler way to derive the same result which we derived from our scalar operations. Now here I have also shown what these activation function operations as well as the linear matrix multiplication operations mean from the perspective of backpropagation. So imagine you have all these layers where in the first pair of layers I and I plus 1 you are having a linear transformation, you are multiplying with W transpose, and the activation function you are applying the activation function element wise. You can show that when you backpropagate and you compute the Jacobian, then that is for the activation layer, it is equivalent to multiplying by the derivative of the activation function element wise. And similarly for the linear layer, when you multiply with W transpose, it is by multiplying with the transpose of W transpose, which is essentially W, weight matrix W, with the activation in the gradient Gi plus 1. So essentially, for most of the common operations, I have created a table of what the forward and backward propagation values are. So here, for example, in linear layer, you are obtaining Zi plus 1, that's the activation of the IS layer by multiplying Zi with W transpose. But then during backpropagation, you can see that you get the gradients in the ith layer by multiplying Gi plus 1 with W. Similarly, for the sigmoid function, you will have a similar formula. Now note that this Zi plus 1, this is element-wise multiplication. This circle with a dot in it, So Zi plus 1 multiplied by 1 minus Zi plus 1. Same for tan A activation. And now there is one here which is, I have also shown for the maximization of inputs. Where do you need maximization of inputs? This is basically used in max pooling. So the key point here is that in all of these cases, it comes down to multiplying the gradients with a Jacobian. Now there are two types of Jacobian. In the linear layers where you're multiplying with a weight matrix, the Jacobians are actually dense matrices. On the other hand, in the activation layers, for example, for the sigmoid layer, the Jacobian is a very sparse matrix. It's in fact a diagonal matrix. So you really don't want to use the matrix form of the Jacobian when you're backpropagating across an activation layer. However, for the linear layers, you would obviously need to perform a matrix multiplication. Now the point is that this vector-wise form of the backpropagation updates is very convenient. This is because many modern hardware platforms like GPUs, they work very well with matrices. And these types of operations, this way of doing the operations is often how it is done in real settings.